The next presentation of the and the last presentation for today's session is from Kostiantyn Kravchuk from EMPA, and talk entitled as Analytical Method for Solid-State Batteries. I would like to also briefly present Kostiantyn. So Kostiantyn obtained his PhD degree from Vernadsky Institute of General and Organic Chemistry of Ukrainian National Academy of Science in 2009. Then he completed postdoctoral research at University of Le Mans in France, the University of Nantes, France, and then ETH Zurich and EMPA, Swiss Federal Laboratories for Material Science and Technology. He now works as a senior scientist at ETH Zurich and EMPA in the Functional Inorganic Materials group of Professor Maxim Kovalenko, and his research interests include all solid-state lithium-ion batteries, novel concept for electrochemical energy storage, and novel materials for lithium-ion and post-lithium-ion batteries. So, Kostiantyn, floor is yours.
Yes, thank you, Andrei. Let me try to share my screen and see whether it works.
Yes, we can see it. Now we can see in presentation mode, so I think, yeah, it is better.
Yeah,
duplicate.
let's change.
Yeah, duplicate. Yeah, now it's perfect.
Okay, great. Let me just find laser pointer. Okay, perfect. Okay, yeah, thank you, Andrei, for this, for your introduction. And basically today I'll try to tell you which methods can be used in general for solid-state batteries, and I will use examples from our own research and also some examples from the literature. So first of all, before I start, let me just say a few words about our battery research at Functional Inorganic Materials Group. So in addition to solid-state batteries, we are indeed working on other type of batteries, so lithium ion, sodium ions, multivalent ion batteries, as well as dual ion batteries. So if anybody is interested in this type of directions, please let me know. So when I try to check basically some review papers and yeah, literature basically which would summarize analytical methods which can be used in solid-state batteries, I found this great review paper in chemistry review, chemical review. It was published last year, and actually this figure, I think it was a figure 1, tells like it gives you a summary of methods which can be used to characterize solid-state batteries in general, starting from the atomic scale, going to interfaces, then like surfaces, and then microstructure and the cell level. You have a lot of techniques here, but I decided to simplify a little bit these methods because we have very limited time today. So I prefer to categorize these methods into like 3 categories. So first of all, one can check, of course, microstructural aspects or morphological aspects of your materials, and also your cathodes or electrodes, generally speaking. And for this, one can use, in addition to classical SEM method, you can use FIB SEM and tomography methods as well. And then you have another category, which is basically dedicated to study long and short range ordering in your material, as well as you can estimate oxidation state of the transition metal and how it is changing as a function of charge. And then finally, you can use methods which can be employed for characterization of surfaces as well as interfaces. I just would like to, before I start talking about all these things, but I just want to mention that in principle, you can make kind of additional characterization of these three pillars into two pillars, which is basically characterization of battery components as they are, or as they are prepared, and also as a function of charge. So basically, when these components are placed inside of your battery, and then you're trying to monitor the changes which are happening as a result of the lithiation and delithiation. So basically, it means that you can characterize your active material or particles of your active material during the synthesis. Is also kind of part of the story as well, because eventually the history of your cathode active material might be impacting the performance of solid state battery as well. So basically having entire panorama of the structural methods and which can be used to characterize materials from the synthesis starting point up to the point where the material is in the battery is very important. So FIB SCM, basically this method is obviously everybody knows, but I would like to emphasize that actually this method is quite handy if somebody would like to investigate interfaces, especially interfaces between lithium metal and solid state electrolytes. Here you see basically on the left side cross-sectional image of LLZO, so lithium lanthanum zirconium oxide porous scaffold, which was impregnated with lithium metal. And from this image, basically, you can get quite good understanding about the penetration of lithium inside of the scaffold, what is the contact area you have, etc., as well as the porosity and tortuosity of this kind of channels which you have inside of this porous solid state electrolyte. On the right side, actually, you have basically two images after two cross-sectional images after focused ion beam milling, which were taken for the same samples which were as assembled and after cycling. So basically, as you know, after cycling or during cycling, during lithium plating and stripping processes, you have you might have formation of voids at the interface between lithium metal and solid state electrolyte, and I think this characterization of this interface from formation point of view of this vacancy or this voids could be quite important to understand the general degradation phenomena which could happen in your solid state battery. Now, of course, milling can be done using different sources, using different ions. So depending on the what you want to reach. So I don't want to go into details. I just want to emphasize the importance of these techniques. Now, there is another aspect which you can do. What you can do with FIB SCM. So you can do tomography as well. And on the right side here, you see basically one cross-sectional X-ray tomography image of NMC LPSCL cathode, which was cycled. And you see electrochemical performance of this sulfide-based cathodes on the left side. And so let me just try to play this video. So basically with X-ray tomography, not X-ray, FIB SCM tomography, you can look into the slices of this cathode and eventually get information about the distribution of your particles and distribution of your conducting additives. For example, and it could be quite important. For example, here you see clearly that you have quite large agglomerates of carbon fibers, but if you would just, for example, take a CM image at this specific place or this one, you might have impressions that in principle this VGCF fibers are not so badly distributed, so you don't have any problems. But so in this specific case, we had issue with the distribution of conductive additives, and it was a reason of the degradation. So advantage of performing tomography measurements over just a FIB SEM cross-sections that you can get again entire information about the cathode microstructure. And the same type of logic can be applied also for observation of lithium voids or cavities between a solid state electrolyte and lithium interface. It is very much pronounced when we talk about interface between oxide-based solid state electrolyte and lithium. So if you make a cut at random place, you might see, you might have impressions that your interface is completely fine, but if you do this X-ray tomography mapping, basically it will be another story, because maybe you'll have a very large region with a cavity in different place. In addition to this type of information, you can also get information about the particle size distribution and also percolation or the connectivity of the particles inside of your cathode, as well as presence of any voids. What I like to also emphasize that here you see a comparison of FIB tomography with other tomographies. So in principle, when you talk about the resolution, you know, FIB tomography has kind of a sweet spot because it is quite precise. So you can have quite high resolution at the level of like basically not tens of dozens of nanometers, but at the same time you can measure quite large samples, so to say, quite large regions as compared to electron tomography or atom probe tomography. So in this sense, it makes sense to use FIB tomography as compared to other tomographies, but of course, X-ray tomography also can be quite handy if we are talking about characterization of large samples, and it's much actually simpler technique, and could be actually used also. Many labs actually have these devices which can do lab-based X-ray tomography. And here you see one example of measurements, X-ray computed tomography measurements of porous L-azoto membrane. Basically, with this tomography, you can identify not just the porosity of membrane, but also how this porosity is distributed along the thickness and along the width of the membrane. And from this type of information, you can get an idea about the connectivity of the pores, about pore size, etc. Now, there are many other techniques, more fancy techniques, which could help you to map your cathode or your anode. I mean, if you're talking about not lithium metal, but any other anode based on alloying type materials, for example. But anyway, so I'm here talking about cathode. So using this sort of chemical imaging, which is based on the operando X-ray absorption spectroscopy. So what you can do here, you can just basically map the changes of the oxidation state of nickel in this case by measuring exhaust under sort of operando conditions. So by looking at the shift, you can identify whether nickel is oxidizing or reducing. And by doing this kind of mapping along the specific X and Y axis, so you can identify which regions of your cathode were basically more oxidized in terms of if you track oxidation state of nickel or reduced. And from this information, actually, you can recalculate, of course, basically lithiation state of your cathode. And I understand the kinetic maybe limitation which you have usually inside of your cathode, especially if the cathode is basically quite thick one. So you might have some inhomogeneities in terms of the lithiation behavior of thick cathodes. And now let's move to the second pillar of methods which is used in solid-state batteries. So of course, one can use X-ray diffraction, but I wanted to give you one specific example which could be interested for you today. It's a kind of a special measurements. So it's a synchrotron X-ray diffraction under a very fast heat treatment, so to say. There was a paper which was published in Science a few years ago, which demonstrated that you can sinter ceramic materials within a minute using a so-called ultra-fast sintering technique. So you basically can connect two metallic rods with by carbon felt, and by applying very high current, one can generate very high jump of the temperatures. You can reach 1000 degrees C within a minute. And this thermal shock enables to sinter basically ceramic materials. And here you see X-ray diffraction measurements, in situ X-ray diffraction measurements of LLZO. Because one thing is to sinter LLZO particles, another thing is to understand what is happening chemically and structurally when you apply this very fast heat treatment or sintering condition. And basically here you see one example what you can do with X-ray in situ synchrotron X-ray diffraction measurements. So you can analyze samples in situ upon a sort of synthesis or sintering. Another basically method which you can use, I think everybody knows this, but just want to mention this, that you can check the changes of the crystal structure of your cathode active material as a function of charge and discharge. And here you see example of lithium iron manganese phosphate, which was charged and discharged. And you can basically monitor as first of all the fraction of the phases which can be formed as a function of charge, and also changes of the unit cell parameter. So it could be quite important, especially when you talk about unit cell parameters. Sometimes it can give you quite good understanding about the changes of the volume, because very often unit change volume can cause the mechanical sort of expansion of the particles, and therefore it might be quite bad for the connection with conductive matrix, and it might lead to the degradation of the battery. Another quite common method which people use to characterize materials is well, X-ray, also absorption spectroscopy, X-ray absorption spectroscopy. And basically with this method one can check oxidation state of your active material or transition metal in your active material. So in this case, for example, we were studying chemical changes which are happening as a result of lithiation and dilithiation of iron fluoride. So by looking at the changes of the H, iron H, you can determine the basically the oxidation state of the iron if you do some like a specific modeling between iron compounds in 2+ oxidation state and 3+ oxidation state. You can determine what exactly is the average oxidation state of iron as a function of discharge and charge, and therefore this information could be quite valuable in order to understand whether whatever you see, whatever capacity you measure could be related to the really redox chemistry of your active material, or it's something to do with some other processes. So in this case, average oxidation state, which was determined by XAS measurements, was very much matching the oxidation state from the electrochemistry, which was indication that whatever capacity we measure, it is really associated with oxidation and reduction of iron. In addition to XANES basically measurements, you can analyze this EXALFS region and calculate coordination environment of the iron and determine the bond distances. In this case, for example, we were interested in bond distances between iron and anions, iron and fluorine. And these distances could be kind of mapped or placed as a function of capacity. So by tracking these distances, we could identify that you can lithiate our iron fluoride up to certain point, and then up to 0.5 moles of lithium you can put inside a formula unit. And then after this point, we could observe drastic increase of the bond distances, which was indication that you have kind of conversion, you start conversion mechanism in this lithiation process. So upon 0.5 moles of lithium, you can insert, which can be considered as formation of solid solution, and then you start forming the secondary phases, which could be amorphous as well. So and finally, you can do total scattering measurements with PDF analysis in order to identify also local changes of the structure. And here you see just example of this kind of ex situ measurements at different stages of charges. And in this case, we specifically proved that you can lithiate this lithium fluoride up to certain stage, up to 3 volts, and you don't have any changes of the local structure basically. But if you proceed further with lithiation, then you change the local structure, which is indications that you have different lithiation mechanism. And this is quite important information if you think about reasons why material is not cycling sort of very well. And also, this total scattering measurements with PDF analysis could be quite important, especially for analysis of amorphous material, because very often materials can be lithiated, but they're getting amorphized. So basically, classical X-ray diffraction could be quite useless to understand what are the structural changes are happening in your sample. And so finally, let's move to the third pillar of our analytical methods for solid-state batteries, so surface characterization. I'd like to start with TOF-SIMS, time of flight secondary ion mass spectrometry. This method is basically can be used to characterize interfaces. Here you see just an example of research which we did on the interface between lithium metal and LPSCL with interfacial layer and without, so with antimony interfacial layer and without interfacial layer. And by doing this maps, we could identify basically the kind of a chemical composition of the surface of these interfaces, and then connect it to the mechanism of improvement of the electrochemical performance, generally speaking. HAXPES, so hard X-ray photoelectron spectroscopy, is a method which is often used to measure surfaces a bit deeper from the surface. So classical XPS methods are used aluminum source, which enable basically to measure or to characterize surface at the level of, let's say, 5 nanometers. So, but with chromium source, one can actually analyze and get information at much deeper levels, which could be quite important without proceeding with sputtering. So this is non-destructive technique for characterization of interfaces. But if you want to sputter, it's also fine as well. So combination of sputtering with XPS enables you to basically understand what is going on, which kind of surface chemistry you have in your materials. And here you see example of LL, the total solid-state electrolyte after ultrafast sintering and after slow sintering. So in this specific case, we basically characterized both surfaces, and we identify that this specific sample had quite a lot of lithium oxide at the surface, which was then the reason why our electrochemistry was pretty bad, and it was completely different if you would just proceed with this normal sintering, because as you see from these measurements, basically one can get pretty clean surface of LZO. So with this kind of sputtering method, you can go quite deep from the surface. So you can basically recalculate sputtering time to sputtering depths. Here you see depths up to 70 nanometer. Of course, it's not very precise, but at least it gives you idea about your surface. Now there is another method which is quite could be quite informative, so-called operando XPS. Usually when you do XPS measurements, it takes quite some time, because you have to scan specific regions, and like as indicated here, and then you can combine them to get the entire spectrum. But of course, during these measurements, which might take hours, basically, your surface could change. So, and you cannot record any changes of your surface during electrochemical measurements. So what can be done, how you can increase this temporal resolution, you can apply so-called snapshot mode, which enables you to monitor changes of your surface within very short time. So you can increase your path energy, and you can use the position sensitive detector. And you can then, of course, not get quantitative sort of representation of your changes, but you can see the qualitative changes general, if you have any shifts or something like this, as in this case. So we in this work try to monitor the surface of the antimony, which was coated on LZO surface, and upon lithiation. And lithiation, we imagine basically XPS. And what we could observe that indeed we could see the shifts of the peaks of antimony, which were reversible, which was indication that we could lithiate antimony, which resulted in the formation of a lithium antimony alloy. So this is just one example of measurements what one can do in order to really track chemical changes under electrochemical conditions. And finally, one method which I find also is quite important is synchrotron grazing incidence in X-ray diffraction, which quite useful to characterize surfaces. Here you see example of these measurements for LZO surface. So basically, we're trying to monitor surface upon heat treatment of LZO. And what you see from here is that we could observe appearance of the peak, this lanthanum zirconate peak, which is quite, let's say, bad in terms of ionic conductivity, which was sort of indicative that we have lithium losses. So it was a confirmation that when you do heat treatment of LZO, you have to be careful, otherwise you might have formation of significant amount of lanthanum zirconate. Right, so with this, I'm done with my presentation, and I am open for your questions.
Yeah. Thank you, Kostiantyn. I didn't see any question, and I asked the audience to ask them, if any. So let's see if it will appear. Meanwhile, I have one question to you regarding lithium metal. So study, because we know that lithium metal is very soft material, and it's difficult to perform, all this in-depth characterization. So which method from all your list would you suggest to use first? And maybe it's more easy to study lithium using this method. So it would be nice to hear your thoughts.
So first of, one can actually study a surface of lithium and spend quite a lot of time just to understand what do you have on the surface of lithium. And on one hand, it might look like, of course, we're gonna see only lithium, but there are some actually papers which indicate that we have to be careful which lithium we use in our batteries. For example, in our group, we are not buying lithium foils, so to say. We are buying lithium rods, like quite thick ones, and we are cleaning these rods, and then we are cutting pieces which are very clean, and then we are making foils from this rod and use them to assemble batteries. So in order to sometimes understand why your lithium is not functioning as good as you would expect it to function, maybe the surface of lithium is maybe contaminated, or maybe you have formation of lithium carbonates on the surface or whatever. So I think it's quite important factor. And of course, from these considerations, you can use many methods. I think XPS it could be quite useful. And of course, if you then combine lithium metal with your electrolyte, you can then investigate, what is happening after a certain number of cycles. And also, I think, XPS, I think it's could be quite useful, because you can just delaminate your both components and try to check what it was formed. Actually, it's a typical method which is used also in lithium-ion battery community. So you kind of you study SCI basically. So
okay, thank you for this answer. I think it's really interesting to hear it from you.